In this lesson, we will be concerned with the problem of determining whether a given n by n matrix is similar to a diagonal matrix. Let us recall first what it means for matrices to be similar. Two square matrices A and B are called similar if there exists an invertible matrix P such that B is equal to P inverse times A times P. Why are we interested with similar matrices? Well, it turns out that similar matrices share a lot of properties. Some of these properties include the following. First, similar matrices have the same determinant. Why is this so? Our hypothesis here is that A and B are similar, so that means that B is equal to P inverse AP for some invertible matrix P. If we now get the determinant, we have determinant of B equals the determinant of P inverse AP. From the properties of the determinant of P inverse AP is equal to determinant of P inverse times determinant of A times the determinant of P. However, the determinant of the inverse is equal to 1 over the determinant of your matrix P. Since these are just real numbers, this cancels out, and therefore we get that the determinant of B is the same as the determinant of A. Another property is that if one of them is already known to be invertible, then any matrix similar to it will also be invertible. Again, we have B is equal to P inverse AP. I will just prove one direction. Suppose that A is invertible. If A is invertible, that means that we can talk about A inverse. A inverse exists. Then this means that we can get the inverse of B by getting the inverse of P inverse AP. And what is this equal to? Recall that you start with this one. When you get the inverse of a product, the order reverses. So we get P inverse A inverse times the inverse of P inverse, which is P. So again, that is P inverse A inverse times P. So the other direction also works that way. If you will start with B is invertible, you can also solve for A inverse. Another property of similar matrices is that they will have the same rank. I will no longer prove this. An immediate consequence of this property is that if A and B have the same rank, then A and B would also have the same nullity. Statement 4 is just a direct consequence of your rank nullity theorem, because let us recall that if A and B are n by n matrices, the rank nullity theorem states that n is equal to rank of A plus the nullity of A, and this is also equal to the rank of B plus the nullity of B. And therefore, if they both have the same rank, then their nullity will also be the same. Next, two similar matrices would also have the same characteristic polynomial. To prove this, suppose again that B is equal to P inverse AP. How do we calculate the characteristic polynomial of B? This is just the determinant of lambda times the identity matrix minus B. I will write B as P inverse AP. And then I will also write I as P inverse times P. Hence, I can write this matrix here as P inverse times lambda I minus A times B. I factored out P inverse on the left and P on the right. And therefore, just like what we did in number 1, This determinant is now equal to the determinant of lambda I minus A, because determinant of P inverse times determinant of P will be cancelled out. And this is precisely your characteristic polynomial of A. Since A and B have the same characteristic polynomials, then they will share the same eigenvalues, because the eigenvalues are just the roots of your characteristic polynomials. By looking at these properties, similarity tells us that we can study properties of a matrix by getting a matrix similar to it, which is relatively simple in form. And what would be an example of a matrix which is simple in form? Those would be your diagonal matrices. Why are diagonal matrices easy to work with? We will see why this is in the next slide. I will be using this notation for a diagonal matrix. When you see this one, D equals diag D1, D2 up to Dn, this refers to the mean diagonal entries of your matrix. So hence your D is the matrix D1, D2 up to Dn. Those are your diagonal entries, and the non-diagonal entries would all be equal to 0. What is the nice thing about a diagonal matrix? What can we say about its eigenvalues? The eigenvalues are simply its diagonal entries. Let us recall from our previous video lecture that the eigenvalues of a triangular matrix are just the entries in the main diagonal. And a diagonal matrix is a special kind of triangular matrix. So therefore, just by looking at your diagonal matrix, we can easily get its eigenvalues. Moreover, the rank of a diagonal matrix is simply the number of its non-zero diagonal entries. Let us recall that the rank of a matrix is equal to the number of its linearly independent columns. But since we have a diagonal matrix, it is now easy to see the linearly independent columns. Those are just the columns with non-zero diagonal entries. What would be the nullity of D? The nullity of D is simply the number of zero diagonal entries. Again, this is just a consequence of your rank nullity theorem. If the diagonal entries of your D are all non-zero, then your diagonal matrix is invertible, and its inverse is also a diagonal matrix whose entries are simply the reciprocal of your diagonal entries. We have seen how to get the properties of a diagonal matrix simply by looking at your diagonal matrix. No computation whatsoever is needed. Hence, we are interested with matrices that are similar to diagonal matrices. Such matrices are said to be diagonalizable. So here is a definition of a diagonal matrix. It must be similar to a diagonal matrix. That is, there exists an invertible matrix P such that P inverse AP is a diagonal matrix. In this case, we say that the matrix P diagonalizes A. Here is an example of a diagonal matrix. If A is given by this matrix, then it is similar to this diagonal matrix whose entries are 1, 2, and 3. And this matrix P here is given by this one. Another example, if your matrix A is given by this one, it is similar to this diagonal matrix whose entries are 4, negative 2, negative 2, and P is given by this. We now go to our diagonalization problem. Let us recall that what we want to know is to determine which matrices are diagonalizable. So, therefore, for a square matrix A, does there exist an invertible matrix P such that P inverse AP is diagonal? The next slide will give us sufficient and the necessary condition for a matrix to be diagonalizable. Here is our big theorem. If A is an n by n matrix, A is diagonalizable if and only if A has n linearly independent eigenvectors. This theorem is an if and only if statement, so therefore we prove two directions. So first, let us prove 1 implies 2. That is, Suppose that A is diagonalizable, and we will show that A has n linearly independent eigenvectors. Since A is diagonalizable, there exists a diagonal matrix D and an invertible matrix P such that P inverse AP is equal to D. Multiplying P on the left side of your equation, we get that PD is equal to AP. Now let P, this matrix P here, your PIs are the columns of P. Let the diagonal entries of D be D1, D2 up to Dn. So therefore, PD here will now become P1, P2 up to Pn times your diagonal matrix. And then we have A times P, where P is P1, P2 up to Pn. If you multiply a matrix with a diagonal matrix, the columns of this product will just be equal to a scalar multiple of your columns here. This one would be D1, P1, D2, P2 up to Dn, Pn, and this is equal to AP1, AP2 up to APN. Hence, if you look at this one is saying that API is equal to DI times PI. This is true for all I from 1 to n. This one is saying that PI is an eigenvector of A corresponding to your eigenvalue DI. This is true for all I from 1 to n. We have now shown that we have n eigenvectors of A. But what we want to do is to show that they are linearly independent. Why is P1 up to Pn linearly independent? Now, since P is invertible, that means that the rank of P is equal to n. It has full rank, meaning to say all of its columns are linearly independent. And that proves what we want to show. So therefore, the set P1 up to Pn is a set of n linearly independent eigenvectors. Let us prove the other direction. Suppose that A has n linearly independent eigenvectors. Let us show that A is diagonalizable. The proof is just the reverse of what we had earlier. So suppose P1 up to Pn is your set of n linearly independent eigenvectors of A. Moreover, let lambda 1, lambda 2 up to lambda n be your eigenvalues of A. And this lambda 1 corresponds to your eigenvector P1, lambda 2 corresponds to your eigenvector P2, and so on. We will now form our matrix P and D. We will form the matrix P, whose columns are your linearly independent eigenvectors. And your matrix D is the diagonal matrix whose entries are lambda 1, lambda 2, up to lambda n. Then what is AP? AP is equal to A times P1, P2, up to Pn, which is the same as AP1 times APn. But since the PIs are eigenvectors of A corresponding to the eigenvalue lambda I, this is equal to lambda 1 P1 and so on up to lambda n Pn. And we can write this as P1, Pn times the diagonal matrix lambda 1 up to lambda n. And this is precisely your PD. Hence, we have AP equals PD. If I multiply P inverse on the left, we now get that P inverse AP is equal to D. Notice that P is invertible because these columns are linearly independent. Hence, we have just shown that A is really diagonalizable. This proof tells us how to form your matrix P. How do we form our matrix P? You just get the set of n linearly independent eigenvectors of A, and that would be the columns of your matrix P. And to form the diagonal matrix D, you just get the eigenvalues of A. So here is what we did. This one, the columns of P consist of the n linearly independent eigenvectors of A, and the diagonal entries of D are the eigenvalues of A. And note that the order of the eigenvectors used to form P will determine the order in which the eigenvalues appear. So for example, let us look at this matrix that we had earlier. A is diagonalizable, and this matrix P diagonalizes your A. Let us call this P1, P2, P3, and let us compute AP1. When we multiply A with P1, we get P1 also. And that is because 1, 1, 1 here is an eigenvector corresponding to your eigenvalue 1. If we compute AP2, we will get 2, and that is because 0, 1, 1, P2 is an eigenvector corresponding to your eigenvalue 2. Here's another example. Now, just to reiterate what I mentioned here, the order of the eigenvectors used to form P will determine the order in which the eigenvalues appear. Suppose I take my D to be negative 2, 4, negative 2. How do we now form our matrix P? Note here that 4 corresponds to this eigenvector, 1, 1, 0, and negative 2 corresponds to this eigenvectors, 1, negative 1, 0, and 0, 0, 1. So therefore here, if I will start with negative 2, I should get an eigenvector corresponding to negative 2. I can either use this or this. So suppose I will use this, 1, negative 1, 0. An eigenvector corresponding to 4 would be 1, 1, 0. This one. And for negative 2, I will use 0, 0, 1. How do we now form the n linearly independent eigenvectors? We can easily get the eigenvectors of A, but we want to make sure that we get linearly independent eigenvectors. So this theorem gives us the answer to that. Suppose that we get two distinct eigenvalues of A, lambda 1 and lambda 2. And suppose that S1 is a set of linearly independent eigenvectors of A corresponding to lambda 1. Actually, we can get S1 to be a basis for the eigenspace corresponding to lambda 1. And similarly, we can get S2 to be a basis for the eigenspace corresponding to lambda 2. Then, what will happen? The union of these two sets will be linearly independent. That is, eigenvectors corresponding to different eigenvalues are linearly independent. So hence, here is now our algorithm to diagonalize a matrix. First, we get the eigenvalues of A. And once we have the eigenvalues of A, we can get a basis for the eigenspaces. Why do we want to get a basis for the eigenspace? So that we can get linearly independent eigenvectors for each eigenvalue. And from this theorem over here, when we get the union of the bases of the eigenspace, then that set will be linearly independent. If there are n such eigenvectors, A is diagonalizable. Otherwise, then A is not diagonalizable. And again, we form the matrix P whose columns consist of these eigenvectors, and the diagonal matrix D will be the matrix whose entries are the eigenvalues of A. For example, let us find a matrix P that diagonalizes this matrix. Step 1, we have to find the eigenvalues. To do that, we will first get its characteristic polynomial. So that's determinant of lambda I minus A. Notice that on my second column, I have exactly one non-zero entry. So therefore, I will get the cofactor expansion along this column. This is equal to lambda minus 2 times the determinant of, delete this and this. You get lambda 2 negative 1 lambda minus 3. This is equal to lambda minus 2 times lambda minus 3 is lambda squared minus 3 lambda minus negative 2. So plus 2. And this factorizes as lambda minus 2, lambda minus 2, lambda minus 1. Since this is equal to 0, our eigenvalues are 1 and 2. Step 2, we have to find the eigenvectors. I leave it up to you to verify that E1 is the span of negative 2, 1, 1. And the eigenspace corresponding to lambda equals 2 is spanned by these vectors, negative 1, 0, 1, and 0, 1, 0. Note that these two are linearly independent, and of course, a non-zero vector is always linearly independent. And therefore, when we get these three vectors, this is a linearly independent set. So therefore, A is really diagonalizable. And therefore, we can now form our matrix P and D. Let us take your P to be this one, negative 2, 1, 1, negative 1, 0, 1, 0, 1, 0, and therefore your D, negative 2, 1, 1 corresponds to the eigenvalue 1. So therefore this is 1. These two columns here correspond to the eigenvalue 2. So we have 2, 2. Now, not all matrices are diagonalizable. For example, let us consider this matrix A here. This is not diagonalizable. Why is that? First, let us get its eigenvalues. A here is just a triangular matrix, so therefore its only eigenvalue is 1. Next, we will get its eigenvector. Again, I will leave it up to you to verify that the eigenspace corresponding to lambda equals 1 is the span of 1, 0. Therefore, we have only one linearly independent eigenvector. But for A to be diagonalizable, we need 2. So therefore, to show that a matrix is not diagonalizable, we can also proceed just like when we are proving that it is diagonalizable, except that we will stop here, wherein we will not be able to form your matrix P and D. Here's another example. Let us diagonalize this matrix. Again, our first step is to find its eigenvalues. compute its characteristic polynomial, which is the determinant of lambda I minus A. Notice that here I have a row which has exactly one non-zero entry, so therefore I will get the cofactor expansion along the first row. This is now equal to lambda minus 1 times the determinant of, delete this and this. Again, I have a row containing exactly one non-zero entry, so I will get the cofactor expansion along the second row. So that's lambda minus 1 times lambda minus 2 times the determinant of, delete this and this. You get lambda minus 1, 10, 0, lambda minus 3. And therefore, this is just lambda minus 1 times lambda minus 3. So this is equal to lambda minus 1 squared, lambda minus 2 times lambda minus 3. Its eigenvalues are 1, 2, and 3. Next, we get its eigenvectors. Verify that the eigenspace corresponding to the eigenvalue 1 is the span of these two vectors. Eigenspace corresponding to lambda equals 2, that is the span of 0, 5, 1, 0. And lastly, the eigenspace corresponding to lambda equals 3 is the span of 0, negative 5, 0, 1. We have 1, 2, 3, 4 linearly independent eigenvectors here, so therefore A is diagonalizable. We are now ready to form P and D. We will take P here to be the matrix whose columns are just the eigenvectors. And therefore D is the diagonal matrix 1, 1, 2, 3, because these two vectors here correspond to lambda equals 1, and these last two vectors correspond to lambda equals 2 and lambda equals 3 respectively. Now, a sufficient condition for a matrix to be diagonalizable is that if it has n distinct eigenvalues. If all the eigenvalues are distinct, then it is diagonalizable. Why is that? That is just a direct consequence of this theorem, because this theorem tells us that eigenvectors corresponding to different eigenvalues are linearly independent. That is, if lambda 1, lambda 2, up to lambda n are all distinct, and if we get their corresponding eigenvectors, let's say p1, p2 up to pn, this set will be linearly independent. So for example, I have this lower triangular matrix, and its eigenvalues are 2, negative 1, 1, and negative 2. Since all of the eigenvalues are distinct, then A is diagonalizable. What about this one? Notice here that the eigenvalues are not distinct. However, this theorem only says that if it has n distinct eigenvalues, then A is diagonalizable. It doesn't say that if the eigenvalues are not distinct, then A is not diagonalizable. So remember that not distinct does not necessarily imply that it is not diagonalizable. To determine really if this is diagonalizable or not, we have to go through the steps that we had earlier. We already know its eigenvalues, we just have to get its eigenvectors. To continue our study of diagonalizable matrices, let us define this one, the algebraic and geometric multiplicity of an eigenvalue. Suppose that lambda 0 is an eigenvalue of a square matrix A. The number of times that lambda minus lambda 0 appears as a factor in the characteristic polynomial of A is called the algebraic multiplicity of lambda 0. So, for example, if you consider this matrix A, here, 1 is an eigenvalue with algebraic multiplicity equal to 2 because it appears twice when we compute it for its characteristic polynomial. The dimension of the eigenspace corresponding to lambda 0 is called the geometric multiplicity of lambda 0. So again, going back to this example over here, let us consider the geometric multiplicity of lambda equals 1. Take note that the dimension of eigenspace corresponding to lambda equals 1 is equal to 2 as well. So therefore, in that particular example, the algebraic multiplicity of 1 is the same as its geometric multiplicity. Here is the relationship between diagonalizability and multiplicity. In general, for every eigenvalue of A, the geometric multiplicity is less than or equal to the algebraic multiplicity. If it happens that the geometric multiplicity is the same as the algebraic multiplicity of every eigenvalue, then A is diagonalizable. Going back to our previous example here, this is the characteristic polynomial of A, lambda minus 2 squared times lambda minus 1. When we computed its eigenspace, the eigenspace corresponding to 1 has a basis consisting of one vector. So therefore, the geometric multiplicity of 1 is 1. And from here, the geometric multiplicity of the eigenvalue 2 is 2. But notice here that the algebraic multiplicity of 2 is also equal to 2, and the algebraic multiplicity of 1 is also equal to 1. So hence, the algebraic multiplicity is the same as the geometric multiplicity for each eigenvalue. And that is the reason why your A is diagonalizable. We were able to form P and D. However, for this matrix here, what is the characteristic polynomial here? The characteristic polynomial is lambda minus 1 squared, correct? So therefore, the algebraic multiplicity of 1 is 2. However, the geometric multiplicity of 1 is just equal to 1. They are not equal. So that is the reason why A is not diagonalizable. Let us consider the diagonalization of matrices and linear transformations. To diagonalize an n by n matrix means that we are to find a basis for Rn such that the matrix of the linear transformation Ta with respect to this basis is diagonal. So for example, let T be this linear transformation represented by this. Let us find a basis for R3 such that the matrix for T relative to B is diagonal. This is just saying that we want the matrix representation of T to be diagonalizable. Notice that your T of x1, x2, x3 is equal to 0, 0, negative 2, 1, 2, 3, and 1, 0, 3 times x1, x2, x3. And therefore, this is my matrix A over here. And this matrix A over here is precisely the matrix we obtained here. We were able to diagonalize this matrix. I just copied the matrices P and D that we obtained earlier, and therefore, what will be the basis B that you are looking for? The basis B that we are looking for will just be the columns of P. The matrix for T relative to this matrix B is now diagonal. Let us verify that. This is our linear transformation. This is just a linear transformation induced by your matrix A. And let us recall that if S is a standard basis, then the matrix representation of TA with respect to the standard basis is just equal to A itself. However, since we have P inverse AP is equal to D, P can be viewed as the change of basis matrix from the basis B to the standard basis S, correct? Because for example, negative 2, 1, 1 is the coordinate vector of negative 2, 1, 1 with respect to the standard basis S. P inverse is now the change of basis matrix from, you just interchange this, S to B. So I will now write this P inverse as change of basis matrix from S to B. A is the matrix representation of TA with respect to S, and P is the change of basis matrix from B to S, and it is equal to a diagonal matrix D. If you look at this one is equal to the matrix representation of A with respect to what basis? Look at this. From B to S, and then S to S, and then from S to B. So therefore, this is the matrix representation of A with respect to the basis B, and that is equal to your diagonal matrix.